We're in 6.2, moving through the probability topics that we're going to need later on to have a somewhat of a feeling for to finish off our stats portion of the class, which is mostly the class. So this section is about an introduction to the binomial distribution. And so our example of something that will follow the binomial distribution is this stoplight problem, with some caveats, as they would say. We take the stoplight problem, which we've done before, but we modify it so there's equal probabilities for each light. And we assume independence. And of course we're counting x. Now we can talk about discrete random variables, I guess. X is the number of stops. So we need independence, equal probabilities, and x is the number of stops. And then we can figure out the possible values for x. There's 4 lights. So you can stop 0 to 4 times. Here's the number of stops: 4, 3, 2, 1, 0. To stop 4 times, you have to stop all the lights. That's the only way. So that means its chance of stopping is 0.2 times 0.2 times 0.2 times 0.2, 0.2 to the 4th. And then for x to be 3, that's 3 stops in one go. So the one go could be any one of these 4 spots: first, second, third, fourth position. And fine. Then all these, though, stop, 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 go. The 3 stops, 1 go. So when you multiply those probabilities together, you get 0.2 cubed times 0.8, no matter which one of these you choose. And there's 4 of them. So that's the shorthand version of that formula. Now we could continue that style of thinking. You have to be a little bit careful. So now we're looking for patterns with 2 stops and 2 goes in them. I hope I got it. There's 6 of them, I know that. I think I got them all there, and each one of them has 2 stops. So it's 2 0.2s in the product of the probabilities, and 2 goes, so 2.8. So 0.2 squared times 0.8 squared, and there's 6 of them. And then for 1 stop, that's 1 stop spread around 4 lights. The rest of them are goes. So 3 goes, 1 stop. There's 4 ways to do that. Each one has 1 stop and 3 goes in it, so 4 times 0.2 times 0.8 cubed. And then here's the probability x is 0. 0 is all goes. No red lights. Chance of being able to go through is 0.8. 0.8 times 0.8 times 0.8 times 0.8 is 0.8 to the 4th. So that's how it looks. You notice that the equal probabilities makes all of these quantities, no matter the order, that have the same number of stops and goes, have the same probability. So that's why the equal probability part is useful. So in that case, instead of having all these be different numbers for the probabilities, they're all the same number, then I just have to count how many there are. We also need independence, so these turn out to be products. Probability times probability times probability times probability, that's independence. So that lets us put these numbers next to it. And then we're counting the number of stops. That lets us decide on what patterns correspond to different values of x. So as long as we had independence and equal probabilities, and we're counting the numbers, then something like this procedure is going to play out. And the only thing left for us to figure out is how these numbers here appear. I guess the coefficients of these patterns. So there could be, you could think there's a 1 here and a 1 here. And you might have seen 1, 4, 6, 4, 1 as a pattern before of binomial coefficients. So we'll discuss that. Basically, the way you find the number of patterns with 2 stops in them is you have to select 2 items out of 4 items to put the 2 stops in. So there ought to be, as you would say, 4 C2 ways. That's what 6 is. So we'll see that. We'll see that happening later on. So that's just our example. Over here, we talk about the features that something has to have in order for the probabilities to follow this style of calculation, which we'll make more concrete in a little bit. We need a fixed number of independent experiments. We need each experiment has to end in success or failure, stop or go. We're thinking the probability of success is a fixed number p, 0.2 for stopping. X counts the number of successes. Success is stopping. We're counting stops. 4 is 4 stops. So in our stoplight problem, the number of experiments is 4. We need independence. We said independence is assumed right here. Okay. Success is a red light causing a stop. Okay, that's okay. Probability of success is 0.2 always. So it's a fixed number p, and we are counting successes, the number of stops. So we've met all the conditions for a binomial experiment, and that means we'll be able to compute probabilities with this style of calculation, and we're going to come up with a formula for these kinds of calculations shortly. So you just have to have patience for that. It's coming. The binomial probability formula is in this section. And now I just have to find my turn off button. Let me just double check everything here. So did we do everything we were supposed to do? The answer is, I sure hope so. I'll see you on the next slide, and here we go.